Hello, statistics. We are starting section 7.2 where we're going to talk more about this normal distribution curve. We are going to learn how to find and interpret the area under a normal curve and how to find the value of a normal random variable if we know what area we want contained. So we talked about z-scores earlier this year, and the z-score was defined as being how many standard deviations an observation is away from the mean. So we're going to continue this idea with the z-scores, and x is our random variable, and then we have mu, the mean there, and we're going to take the difference between those and divide by sigma, the standard deviation. Now, in a normally distributed curve, we can assume that the mean will be 0 and the standard deviation is 1. Then z will have this normal distribution. So the normal distribution curve would look like this, as we looked at yesterday, where our mean is right in the middle at that peak. And so 0 is in the middle at the peak, and then our standard deviation of 1, taking a step out to each side, and those would be those inflection points. And then we also talked about how we could follow that 68, 95, 99.7 rule, and assume that 68% of the data would lie between -1 and 1, and also that there's a symmetry here, so that 50% of the data would lie below 0. Now z could be any random value along that x-axis. So z could be -1, meaning 1 standard deviation to the left, but z could be a different value, and here it looks like z is maybe -2, but maybe not an exact integer amount. So we can use tables to find the area to the left of any specified z-score. So for example, IQ scores are normally distributed amongst the population, and they're said to have a mean of 100 and a standard deviation of 15. So if we know someone has an IQ score of 120, we want to determine how far above the mean are they. So 120 minus 100 divided by 15 gives us a z-score of 1.33. They are 1.33 standard deviations above the mean. If we're then wondering what percentile are they in, what percent of the population is that IQ score higher than the rest of the population, we can use tables that look like this. So along that left-hand side, we're going to start with z equals, and we're going to go to 1.3, and then we're going to go over to the 0.03. That would make 1.33. And we see the entry in that cell is 0.9082. So about 91%. So that means if someone has an IQ score of 120, we would say they're in the 91st percentile. Their score is higher than 91% of the population. That is the area to the left under the normal curve. So again, as we look at this normal curve now, that z-score would be over on the right-hand side because it's above the mean. But so that blue shaded area then for that representative z-score would look like this. So 115 would be 1 standard deviation away because the standard deviation was 15. 120 is more than that, 1.33. And that blue area is what the chart told us. And then if we wanted that area to the right, we could use the complement subtracting from 1. So these are the exact values. So when we use that 68, 95, 99.7 rule, those are rounded off. So technically, between 1 standard deviation below and above, it's actually 68.26%. But we just round that off and call it the 68, 95, 99.7 rule. So we can still use that empirical rule for approximations if our score is exactly on one of the standard deviation lines. But now that we have these tables, we can find more precise calculations of the area under the normal curve. I'm also going to show you how to use StatCrunch to do this. So in this example, if we wanted to find the area under the normal curve to the left of z is -0.038, over on that left-hand side of this chart, we're going to go to z is -0.03. We're going to go over to the cell that corresponds with 0.08, and that entry is 0.3520. That is the area to the left of that z-score. This chart always tells us the area to the left. If we want to know the area to the right, we need to use the complement. So that is what this slide says as well. If we want to know what the area to the right is, we're going to do 1 minus the area to the left, that complement probability. So if we want to find the area under the standard normal curve to the right of z is 1.25, I can look in this chart for 1.2 and go over to the 0.5, and I find 0.8944 would be to the left, so 1 minus that, 0.1056 would be to the right. If we want to know the area between two values, it gets a little trickier. So we'd want to know the area to the left of the bigger value, but that's going to overshoot, so then we'd want to subtract from that the area to the left of the smaller value, and that should then leave the area between them. So we would need to look up both of those values within the chart and take the difference. So here we're finding the area to the left of the value. We can shade that in. We can convert it to a z-score and then use the z-table. We can also use technology, and I will show you how to use StatCrunch for the technology there. To find it to the right, we're going to need to do that complement. So these two slides are just a summary of our types of problems. To find an area between, again, a summary, we're going to take the difference. So if I wanted to find the area between these, I'm going to take that larger one, the one that's further to the right, and find the whole area to the left of that, but that would overshoot. So then I'm going to subtract from that the area to the left of x1, the smaller value, to get rid of that tail and be left with just what is between. So now if I want to find what the value of a random variable is, and I know the area, we're going to use that chart backwards. So we're going to use the chart to find the z-score that represents the area. So the GRE test is a test that students may need to take to get into a graduate program. I did not have to do this for my graduate program, and I may have looked for a program that didn't require it because I was not interested in taking that, but it's kind of like an SAT or ACT, but for graduate school. The combined score is normally distributed with a mean of 1,049 and a standard deviation of 189. So let's say that for a student to get into a particular program, they needed to score in the 85th percentile. Well, what score are they shooting for then? So if they see in the documentation they need to be in the 85th percentile, what score do they need to shoot for? So we're not going to use this formula. Instead, we're going to look at, okay, so there's no chart here. I thought there would be a chart in here. So what we would need to do is look at a chart and find the 85% or the 0.85 within the chart, and it says the z-score is 1.04. Let me see if I can get one of those earlier charts if it shows. Yeah, okay, so this one does. So now that we know it's 1.04, it's a little bit of cheating, but what we would want to do is look within one of these charts and find the cell where we see as close as we can possibly get to 0.85, since we're going for the 85th percentile. And so we just kind of have to read across the rows until we find it. And right here I see the one that is as close as I can get to 0.85. And then I'm going to read off, where did that come from? It came from 1.04. So that would be our z-score on that. So that's the z-score, but what does that mean about our student?